so on to the maths for Doppler effect. Now the two equations on the left you already know, I hope you should know them. We've been dealing with them since grade 10. So first one, velocity is frequency times wavelength. You should know what the units for that are. I'll verbally remind you if you want to write them down. Velocity is in meters per second, frequency is in hertz or per second, and wavelength is in meters. And then down here, we've got velocity is equal to displacement over change in time. Okay, so change in position or displacement over change in time. Velocity again, meters per second. Displacement is in meters, time is in seconds. Okay, now the one on the right, this is our new formula. This is the Doppler formula. Okay, the reason I've written those there is because they will occasionally crop up in questions to do with Doppler. Okay. But this is the main Doppler formula, and it says the observed frequency, okay, the frequency that the listener perceives is equal to the velocity of the wave plus or minus the velocity of the listener, so if the listener is moving, over, again, the velocity of the wave plus or minus the velocity of the source, if the source is moving, and then multiply that by the frequency of the source. So this is the actual frequency of the wave. So if they gave you the wavelength and the speed of the wave, and you wanted to work this out, you would use this formula, okay? This formula is for the actual frequency. I'm actually going to put you, that's Fs. That's the frequency of the source, not the frequency that the listener gets, unless the listener is experiencing the actual frequency, so he's passing by the object, or the object is passing by him, or they're both stationary. Okay. Now, when you you've actually got the explanation of what each of those variables is on your notes, so I'm not going to write them down. What I am going to do though is draw your attention to something incredibly important in this section. It's probably the trickiest part of using this equation, but all you have to do is learn it off by heart, and then you'll be fine. Okay, and that is velocity is a vector. Usually, you are allowed to pick your own positive direction, okay? But in this case, you have to use the sign convention that I'm going to show you now. You can't decide whether, if I have a stationary source and my observer is approaching it, you can't say, let's let approaching be positive, or let's let approaching be negative. That's not up to you, because the reason why it's important is because if our observer were approaching our source, then the perceived frequency must be higher than the actual frequency, right? Which means we need to take this frequency and multiply it by a number greater than 1. This fraction would have to be greater than 1. Now, the only way to make this fraction greater than 1 is if the denominator is bigger, the numerator is bigger than the denominator, which means we would have to make the velocity of our listener positive if it's approaching. Okay? Now, if it's the other way around, if our source is moving and our observer is stationary, if our source is moving, let's do it the other way around. If our source is moving away from our observer, that means our observer should be perceiving a lower frequency than the source, right? So FL should be less than Fs. The only way for that to happen is if we take Fs and multiply it by a fraction smaller than 1. So to make this fraction smaller than 1, the velocity of our listener will be 0, he's stationary. So the denominator must be bigger than the numerator. Only way for V and Vs to be bigger than V is if we plus Vs here. Okay, so it's up to you. You can think it through logically like that every time, or you can just learn off by heart that in scenario 1, okay, so scenario 1, remember that's when your source is moving, then the velocity of your listener is 0, okay, always. And now if your source is approaching the listener, okay, if your source is approaching the listener, then you're going to go and make it negative. Okay, so if your source, sorry, I had to cheat there because my brain stopped working. Okay, if the source approaches the listener, then the velocity of the source is negative. Let's just say it's less than 0. Okay, it's negative. But if the source is moving away from the listener, so this is the example I explained when I was explaining it, then the velocity of the source is greater than 0. Okay. However, if we've got scenario 2, so if we have a scenario where the source is stationary and the listener is moving, then the velocity of the source will be 0, right? Because our source is stationary. And if our listener is approaching our source, okay, then we'll say that the velocity of the listener is greater than 0. It's the opposite to scenario 1. Okay, for scenario 1, if it's approaching, the velocity is negative. For scenario 2, approaching, the velocity is positive. Okay, and then if the listener is moving away from the source, then we will say that the velocity of the listener is negative. Okay, so up to you. Either you can learn this off by heart, or you can go ahead and logic it out each time. Think, does FL need to be bigger than or smaller than FS? Based on that, must this be a fraction bigger than 1 or less than 1? Based on that, must I add or subtract at the bottom or add or subtract at the top? Okay, so it's up to you which one you want to do. Okay, so I'm going to pause you there. We're going to do a quick example, and then that's it. This is actually really, really quick. There's very little maths they can ask. Okay, guys, here is our example. Sorry, it's a lot to write down. So we've got Tristan driving his fancy drag racing car at an unknown but very high speed. He hears another car's alarm go off. The sound has a wavelength of 0.68 meters and travels at 340 meters per second. And Tristan hears the alarm at 300 hertz, and we need to determine the frequency of the wave. Okay, so just quickly, this 340 meters per second, that is, it's not, okay, so you know the speed of sound in light, that constant c, 3 times 10 to the 8. So that is always the speed of sound in light. What did I say? The speed of light in air. I don't know what I said earlier, sorry. The speed of light in air or a vacuum is always that constant c. Now, because the speed of sound is much smaller than the speed of light, that means that any change to this value is much more significant. Okay, now this value will change depending on, so we did speak in grade 10 about the fact that sound is a longitudinal wave, and longitudinal waves need a medium in which to move through. And the denser that medium is, the faster that the sound will move through it. Okay, so we spoke about the fact that when you're in space, when you're in a vacuum, you won't hear anything. Sound can't travel in a vacuum. And the more dense your medium becomes, the faster the wave will travel. So this 340 meters per second, that will generally be the value that they give to you for the speed of sound in air. But bear in mind that it won't always be 340. So if they don't give it to you, don't assume that it is. Okay, but that will usually be the number. Okay, now let's unpack what we've got. We know that he hears the car's alarm go off. The sound has a wavelength. Okay, so we've got the wavelength of the wave. We've got the speed of the wave. And we've got that Tristan hears it at 300 hertz. So that's not the frequency of the wave here. That's the perceived frequency, the frequency of the listener. So those are the 3 pieces of information we have. Now, they want us to determine the frequency of the wave. Okay, so we've got 2 formula that have, so this the frequency of the wave, that's the frequency of the actual source of the wave. So we've got 2 formula we can use there. We can either use the Doppler formula, or we can use V equals F lambda. Now you'll see that the only formula we have enough information to use is the one that says wave speed equals frequency times wavelength. Okay, we know the wave speed is 340. We want the frequency of the wave, and we have its wavelength. Okay, and from that you will find that the frequency is equal to, I want to say 500. 340 divided by 0.68 is 500 hertz. Okay, so this car alarm has a frequency of 500 hertz. Then, question B. Is the source of the alarm in front of or behind Tristan, and why? Okay, so let's draw a little picture of what's happening. We've got, we can't draw a picture because we don't know if it's in front of it or behind it. But 2 options. Either we've got the source of the sound and we've got Tristan moving towards the source of the sound, or we have the source of the sound and Tristan moving away from it, right? So this is if it were in front of, and this is if it were behind. Other way around. Yeah, this is if it were in front of him, this is if it were behind him. Now, if it were in front of him, the perceived frequency would be greater than the actual frequency. But if he were moving away from it, then the perceived frequency would be less than the actual frequency, remember? So let's compare the two. The actual frequency is 500, the perceived frequency is 300, which means he is hearing that sound at a lower pitch than what the sound actually is. For that to be happening, he must be moving away from the source, which means the source of the sound is behind Tristan. Okay, so we can say it's behind him. Okay, and why is because the perceived frequency is lower than the actual frequency. Which means he is moving away from the object or away from the source. Okay, now this would normally be a 2-mark question, and you would get your 2 marks, so you would get your 2 marks for saying where it is, and then it's honestly good enough to just say because the perceived frequency is lower than the actual frequency. So this little, which means he's moving away from it, you don't even need to include that. That's just for your benefit, so that you understand if it's behind him, it means he's moving away from it, and that's why he's hearing a lower perceived frequency. Okay. Then, question C, determine how fast Tristan is driving. So, 2 options there. We can either use V equals delta x over delta t. We don't know delta x or delta t though. Not going to work. We do have the Doppler effect equation though. And in the Doppler effect equation, there is a space for the velocity of the listener. That's what we want here, the velocity of the listener. So we're going to use Doppler. Okay, and I think I must just switch it down a little bit. Oops, somehow. There we go. Okay, so we're going to use the Doppler effect to work this one out, the Doppler equation. And the Doppler equation says that the frequency that the listener experiences is equal to the velocity of the wave, the actual wave, okay, plus or minus the velocity of the listener over the velocity of the wave plus or minus the velocity of the source, all multiplied by the frequency of the source. Now, we have to both substitute in our values and make sure we're using the correct sign now when we use this formula. Okay, so frequency of the listener, they told us that one. Okay, we've got, he's hearing the sound at 300 hertz. The velocity of the sound wave, they told us that as well, that's 340. So I'm going to put 340 at the top and 340 at the bottom there, because that's what V is, the velocity of the wave. Then the velocity of the source is 0, so you actually don't have to. If you want to, you can. Okay, so I'm doing it in dotted lines. You can substitute in your 0, but there's actually no marks given for substitution of 0. Okay, you're also welcome to just leave that term out. It means the same thing. But now at the top, the velocity of the listener. This is what we're after, right? Now, are we going to say plus VL or minus VL over there? Well, we know he's moving away from the source, okay? So if he's moving away from the source, that means FL must be less than Fs. The only way for that to happen is if Fs is multiplied by a fraction smaller than 1, which means my numerator must be smaller than my denominator, which means I must subtract something from my numerator. Okay, so you can logic it out, or you can just have learned the fact that if I have an object moving away from my source, I subtract its velocity. Okay, and then we input our Fs, which is, we worked it out in question A, 500 hertz. Okay, and that's it. Now we just solve for VL. Hoping that's nice and easy. Sib, I need you here. I've forgotten how to use a calculator. Okay, times 340. And then 340 minus that answer. So he is moving at a ridiculous speed. Okay, his velocity is 136 meters per second, which just for funsies, let's convert that to kilometers per hour. He's flying. Okay, so it's 136 meters per second. So we divide by 1,000 and then multiply by 60 twice. He's going at 4. Hey, you got a serious fine coming your way. He's going at 489.6 kilometers per hour. Good luck with that one. Okay. So yeah, that's basically it. That's Doppler. In addition to this sort of thing, okay, there's still light. We must still do light. So if you are now going to start doing past papers and you start seeing things about red shifting and blue shifting and the expansion of the universe, don't panic. That's still coming up. But in terms of sound, we are done. Okay. Usually, in an exam, you'll have a multiple choice question, one multiple choice question on Doppler where it's either about the sound or about the light. And then the extension question, the calculation question, will be on the other one. Okay, but there's less to talk about with light. So normally the multiple choice will be on light, and then the extended question will be on sound, where there's some maths. They could ask you to explain some other things. They could ask you to draw a graph. There is a question that I've asked you to draw a graph. I'm not going to show you how to draw that now. I want you to try and think that through. But yeah, this is basically it. And I'm rambling. Okay, good luck. Let me know if you get stuck, please.